Okay. Okay. So now today we'll do the horizontal acceleration. Just now. Okay. So in case of horizontally accelerating vessel, we can start with the vessel first of all. So you can see this is the liquid which is filled in this vessel, and the vessel is open from the top, and there is some gap, some space. So this is of course three-dimensional, but what we are looking is the two-dimensional view. So this you can say as the height as h, and the length of the base you can call it L. And definitely there must be some width of the vessel which we don't show like this. It must be something like this. Okay. So the width we can ignore. We can understand it's there. And the gravity is acting, of course, downward. We all know this. Now, the moment you accelerate, the entire liquid has to accelerate. Okay. So the moment we start accelerating, now this is the scenario in the very beginning, but afterwards, let's say things changed. And once the acceleration will start towards the right, the liquid will appear like this, assuming the equilibrium is achieved in the frame of the vessel. So now, by tilting like this, what will remain the same? What remains the same? So when the liquid will tilt like this, which quantity will be conserved? Volume. So the first thing that we need to always write as an equation that called the conservation of volume, because no liquid is spilling out of the vessel. Okay. So we can call it H1, H2, and the base as L. And now you can conserve the volume, but volume conservation is as good as conservation of area, right? So the first step of solving any problem of accelerating vessel is conservation of area. Basically, you can say volume. So we have taken some dimension in the right side, H1, H2, which was not actually given, but we have assumed. On the left, we have everything known to us, H and L. So we can add area is HL, which is the area of rectangle. And on the right hand side, you can see it's a simply sum of the, like it's a trapezium, you can add the sum of parallel sides into separation. And this gives us one relation that the sum of the height is exactly 2h. So this is the first relation that we need to keep in mind. And this is, there is no physics right now, it's just conservation part. So now the question was like, if the vessel will accelerate towards right, why the liquid will be in this shape? Like why it will tilt backward?
Pseudo
So of
force
course,
will act.
yeah, you can say that it's a pseudo force which is doing that. But the other way of thinking is that if I consider uh, an elementary volume of liquid within the liquid itself, and let me make a maybe something like this. Yeah. So we can say that this elementary capsule is also accelerating towards right. And now to accelerate towards the right, you need to have some net force. So if I take the left end of the vessel as the origin, and if I draw the like something, so if I call this is x, and if I call this is dx, then on which side of the capsule the pressure must be bigger, the left or the right? What do you expect? So on which side of the capsule the pressure is more, the left side or the right side? Tell me.
Left side.
So if we say the pressure at the left side is P,
The right side.
the pressure on the right will be P plus dP. And definitely the left must be bigger than the right, then only it can accelerate towards right. Understood? So the whole capsule is accelerating towards right. Do you realize this?
So, but the water is accelerating towards the left, no?
Who said? Well, the entire vessel is going towards right. How the water can accelerate left if the vessel is going right? I don't know. Okay, I'm not applying any pseudo force for your kind of information. There is no pseudo force. We are solving in the ground frame reference. So can we say the capsule is going right? Yes or no?
Yeah.
Yes.
And if the capsule is going right, then which side the pressure should be bigger to produce the acceleration towards right?
P.
Left side. P.
Hmm? Yeah, so the left side pressure should be bigger, then only it can push and then create the acceleration. So if we talk about the net force towards right, so we can say net force towards right equals to mass into acceleration. And let's apply this formula for the capsule we have. And what is the capsule we have? So we can write P minus P into area, let's call dA as the area of cross section. I mean, yeah, I hope you can understand what's dA. All right, so PdA minus P plus dP into dA equals to mass dm, because that's capsule into acceleration. So if you simplify this, what you get? PdA minus PdA minus dP into dA, and dm is what? Density into volume, which is rho dA dx. It seems like all the dA will cancel out, so what left with is only minus dP on the left side. Okay, this is anyway cancelled. And on the right hand side, what you can get is rho A dx. And from here we get the first derivation, that the pressure gradient is minus rho into A. This is called pressure gradient. And the rate at which the gradient will decrease is rho into the density into acceleration. And minus is saying that as you progress towards x direction, pressure will drop. And that is quite evident from the diagram, that as you go towards right, the water level above the point will be lesser and lesser and lesser. So the highest pressure will be on the leftmost side. That's origin is the highest pressure point. And if I say A, B, so inside the liquid at the bottom, O is the highest pressure and A is the lowest pressure, and that is also justified by the height of the liquid column you can see above it. Which means pressure can be analyzed in two ways. One is horizontal, other is vertical. Now, no matter how you analyze the pressure, the answer must be same. And therefore, as you go right, pressure will decrease horizontally, which is actually manifested by the decreasing height of the water. And that is why we are getting a slanting shape of the water. So does it make some sense to you guys? Maybe, may not be.
Yes, sir.
Okay. So this was the basically pressure analysis, and that we need to keep in mind. And why pressure analysis is required? Because the dP V is something called pressure difference, and that is the cause behind the buoyancy. So whenever we say buoyancy, buoyancy is developed due to the difference of pressure. And now you can see that we do have a difference of pressure even in the horizontal direction. Therefore, you may expect a horizontal buoyant force. And now you can see that the pressure is on the right more than the left. So the pressure difference is towards the right. So can we say the buoyancy will be in which direction? Right or left? So how the pressure will create the buoyancy? Towards right or left? Tell me, guys.
I.
So the pressure difference is the pressure is more on the left and less on the right. So the net pressure is towards the right, and therefore we can say the buoyancy must be in the right direction. Apart from the pressure that we already have in the vertical direction. Understood? So we can also analyze the pressure in the vertical direction. And what we are trying to do is we are trying to prove that the surface will be slant and flat, like it's a straight line in 2 dimensions. So let me do the vertical pressure analysis, which we all are aware of already. Okay, so let's try to analyze why this is the case. So if we have the capsule that we had drawn earlier, look at the vertical length of the capsule, like how much water level is here. And you can clearly see that the pressure at here and pressure at this point must be, I mean, like not pressure, the level from the free surface to the capsule drawn, if this is some value, let's say y, then this is value y dash. They are not same, right? And y dash is small. So definitely if you try to travel from vertically downward from the atmosphere towards this end, the pressure will be how much? We can say pressure will be P ATM plus rho G y dash, correct? But on this side, the pressure which you will write is P ATM plus rho G y. Yeah. And that is justifying the claim that we are making, that the pressure on the left is more and the right is less. And it is also true vertically. And now the question is, the gradient, the decrease, the rate at which this is decreasing turns out to be a constant. So whenever a slope is constant, what you get is a straight line. But let's prove that mathematically. So, so what you can do is we can do like this. Let's say this is y, this is dy. Okay. So if you write the again simple equilibrium condition of this elementary capsule, what is now in vertical direction. So it's good to good to make a vertical capsule just to understand the pressure gradient. So what we can say is that pressure, if the pressure here is P, sorry, from here bottom we are going. If the pressure here is P, then this pressure is P plus dP. Okay. and gravity is pulling downward. So this will have the value dmg. That's like fbd. Okay, and I can do separately. So the force will be pda from the bottom. From the top, it is p plus dp into da, and the gravity is rho dv, which itself is dA into dy, the density into volume into g. Okay, and then you can add for equilibrium. The upward force is balancing the downward force, so upward force is only one p dA, and that is balancing the downward force, which is p dp into dA plus rho dA dy into g. And in fact, we will cancel out. So what we are left with is 0 equals to d plus rho g dy, and this is again giving us the same, the pressure gradient relation, which is minus rho g. Okay, so dp by dy, what we are getting is minus rho g. So now we have the two relation, dp by dy is minus rho g, and uh, dp by dx is also minus rho a. So if you use these two equations, you can prove that dp by dx upon dp by dy is equals to minus rho a upon minus rho g, and therefore what we get here is dy by dx is minus is plus basically a by e. Understood? So you can see that we have a slope which is turns out to be constant. So this is a rigorous proof that the slope is constant, and therefore we can say the tan of slope is a by g. So we'll do it by some other method, but this is just a rigorous like pressure analysis, and this theta turns out to be exactly this value a by g. But here the value a by g is more like vectors. So the g is negative and a is a positive number. So it's basically ax by ay, and ay is like minus g. So anyway, this is a value by a by g. What I was trying to prove that the surface will be flat, and in some question you will also come across finding the pressure gradient. They may ask you how is the pressure gradient, what is the value. So because we have two types of pressure gradient, one is vertical and other is horizontal, which is now claimed here, proved here. So as you go up, the pressure will decrease. So definitely the pressure at the bottom is more than pressure at the top, which means the buoyancy will be upward and buoyancy will be right. So in this entire diagram, what is the actual buoyancy? So if we have a volume V, then we have two buoyancy, and buoyancy is very simple. The pressure difference into area, basically it becomes just equals to what to say. So like here we have V rho G. So here the same thing will become V into rho into A, which is like multiplying volume with pressure difference, sorry, pressure gradient gives us the bond force. So these are the pressure gradient. So one pressure gradient is upward, so that's why we have the vertical buoyancy. So we can say FBY, and other is the pressure gradient which is horizontal. So we have the horizontal buoyancy which we call FBX. So in case of horizontally accelerating vessel, the buoyant force will have two components, horizontal and vertical both. And therefore, if you want to write the net bond force, you have to write something somewhere here. And two terms are common, as you can see, which is V and rho. And this is definitely under root of A square plus G square. So this we write as V rho G effective. And that is what we know. G effective is something like this. Okay. So basically, the value wise is G effective, and why it is so. So again, we can do it by the pseudo force concept. So if you choose any point P here, it will have two force acting. One is the gravity, other is the pseudo force. So the resultant force on this particle will be always in the right angle to the free surface. That's the rule. In fact, there is a simple way of understanding the concept of free surface. A free surface is a surface at which there is no tangential force present. That's why it's called free surface. If we have also learned in the surface tension while studying the angle of contact, so the free surface always remain perpendicular to the net force. Anyone remembers this? No one. Okay, that's all. So that is a property of free surface. If a surface is free surface, then there is no question of tangential force present. So the net tangential force must be zero. That is the takeaway from this concept of free surface. So of course these are some rigorous derivation, but we can go back and we can do it in a simple manner. This is how we study. So we will study with the help of the concept of free surface. So let me just do this diagram without making it rigorous. So imagine a particle on the free surface. And we know that this particle is at rest in the vessel frame. So this is at rest, as you can see. And if I say the mass of this particle is dm, some elementary mass, so the weight will be dmg like this. And because this particle is in the frame of the vessel, vessel itself is accelerating. So what we'll do is we'll take the vessel as our frame of reference. And in the vessel frame, we can see clearly that this is experiencing a pseudo force dm into a towards left. And if I say this is theta, this is also bound to be theta. And what is the status of this particle? The status of this particle is that it is at rest in the vessel frame. So the rule says that for any free surface, the net tangential force must be zero, which means the net tangential force must be zero in vessel frame, which means dm into a cos theta, so dm into g into sine theta, and they must be balancing each other, right? Is this clear?
Yes.
And you can clearly see that the tan theta is how much? A by g. So whenever you are solving a question in which you want to find the relation between the A and the G, the rule is simple. You just write the net force along the free surface equals to zero. We have proved mathematically that in case of, uniformly accelerating vessel, the slope will be flat, and therefore it's very easy to derive the things. Now the rule is the buoyant force always act in the direction perpendicular to the free surface. So it means, now let me do once again somewhere here. So the net buoyant force will have the fixed direction. So whenever we talk about the net buoyant force, it's simple. So if this is the free surface, because of the acceleration of the vessel, this is the net buoyant force, and that's why we have the two component, as we have seen also. So this is always right angle, that's always true. And this angle will be how much? 90 minus theta, I think so, correct? Isn't it? And therefore it will have two components, AB, and the formula for this will be what? What is the FB? V rho, earlier we used at G, we'll just make it G effective. And G effective we have done in the laws of motion many times. So G effective in this case is under root of A square plus G square. That's very simple solution. And tan theta is, so if you want to represent the net value, this is the answer. This is the net value. If you do not want to write net value, you can write the component value. So if you have something here, then buoyant force will be, either you can write V rho G here and V rho A here. This is totally up to you. Either you choose this or these two. Are you getting my point? You cannot take both. So either you represent the two separate buoyant force, V rho G and V rho A, because of the different direction of acceleration, and so on. And if you convert, I mean, if you take the component of the G effective along the horizontal, it is exactly the same answer. Okay, so this is A, this is G. In the frame of the vessel, this is like this, and net force we call it G effective, and it's theta. So tan theta is A by G. This is certifying. So G effective cos theta is G, and G effective sin theta is A. So everything becomes automatic. So if you take the component of buoyant force towards horizontal direction, FB cos 90 minus theta is AB sin theta, which is V rho G effective sin theta, and G effective sin theta is A. So that is a buoyant force. Like if you want to write the buoyant force in horizontally accepting vessel, you write two components separately, vertical and horizontal. That is a better way of solving it. Okay. Also, some points which we need to take care of is that in case of accelerating vessel, the pressure will vary if you move perpendicular to the free surface inside. Okay. So in which case the pressure will not vary, or what will be the shape of the isobaric surface? So isobars, we have to draw the isobars. So to understand the concept of isobar in this case, so if this is the free surface, which means if you travel along the free surface, there is no pressure difference, and therefore any line which you draw parallel to the free surface, so these points are like if you choose multiple points on this surface A, so each surface represents one particular pressure. So this will have some pressure P atmospheric. So if I say this gap is H, so what is the pressure at this level? P ATM plus rho G effective into H. Understood? And the
Yes.
pressure at all these points will be same. So PA, PB, PC all be same. Only when you move parallel to the free surface, pressure will change. If you move parallel to free surface, if you move away from the free surface and parallel, so any surface which is parallel to free surface will have one pressure. They will maintain one particular value of pressure, and that's why these lines are called isobars. So we have discussed the bond force, we have discussed the pressure analysis. So let's go back to the problem that we started with. Okay. So how to solve any question of accelerating vessel? There are two steps in every question. One is, conservation of area. Okay. Another is called the relation between the A and the G. So, okay, once again. So earlier it was flat, and if you remember, it was having the value. So initially, the liquid level was something like this, and this was basically H, and now it is tilted now. And what is very interesting is that when it will tilt, in this case, in fact, you can also remember that the center means the same. So it exactly goes below the center and above the center. Like on the left, it goes above, and right, it goes below. So center doesn't move. It just like it is like a pivot, and it it spins around this pivot. Anyway, so H into L, which is the product of this is a rectangle. So this is area. We have already done this part. So I'm writing directly. So H1 plus H2 turns out to be 2H, right? This is the one equation. Step 2 is this theta, you can assume this slope as theta always, that's the rule. And then try to write tan theta in terms of geometry. So in terms of geometry, what we can write? So tan theta is equals to how much? So you can write S2 minus H1 by L, right?
Yes.
And the third is the tan theta in terms of acceleration that we already know. The tan theta is how much? A by G. So you can compare these two. And so you can say that H2 minus H1 by L, which is the geometrical slope, is equivalent of A by G, which is the physical slope, okay, like the way we calculate. And therefore, we have two equations, two unknown. We can solve. So the difference is this much and sum is 2H. You can solve these two. And it's very easy to solve and get the answer. Oh. If you add these two equations, what you get? 2H2 equals 2H plus L by G. So H2 is H plus L by 2G. And H1 will be H minus the same term, L by 2G. Understood? And how to analyze the pressure to go from anywhere to, let's say this is A, B, C, D. So pressure is very simple. At A we have the atmospheric, at D we have the atmospheric. Okay. So at B, how much is the pressure? Let's say if I ask what is the pressure at B, we can say it's a PA plus rho G H1. That's it. Because we are moving vertically downward. Now to write the pressure at point C, we can write in 1,000 ways. Let's say, suppose I know the pressure at B and I want to write the pressure at C. So how to write it? So if you remember, the pressure will grow as you go backward. So it will be rho AL. Why? Because if you remember, the pressure gradient was rho A, and how much we have moved backward. So we have moved backward by L value. So it will grow by this much value. So on the along the direction of acceleration, pressure decreases. So against the acceleration, if you move, pressure will increase. That's the rule. Is this clear? I don't think so. Huh? Let me do it again.
No, can you also?
So if you remember that the delta P by delta X, if I choose the origin here and if I choose, say, this as X axis, if I call it Y axis, so delta P by delta X means inside the vessel, because we are writing the frame, is minus rho into A. So delta P is how much? If I integrate, so at origin when X is 0, let's call it P naught just by name. So when it is X, let's call it Px. So convert P minus P naught equals to minus rho X. Is this okay?
Yeah.
P is how much? P naught plus rho X minus rho X, right? So as you go away from the origin, means if you go along the acceleration, the pressure will drop by this value. That's the idea. So if you go against, if you go backward, the pressure will increase or decrease? It will increase. By what value? So it's rho into A into how much you travel horizontally. X. Is this clear? Yes or no?
Yes, sir.
Okay. So you can always write the pressure. I mean, you can always write the pressure in the horizontal direction easily. So the rule is simple. If you move along acceleration, subtract rho ax, and if you move against acceleration, add rho ax, and that is what you need to just remember. Okay. So far, so good. Or any
Understood.
doubt? Hmm?
Understood.
Okay. So, so generally this question comes as a tube problem. Okay. So now you can see there's a tube, and you can again say the same thing. This is H. Let's say this is H. So here the area you will not conserve. What you conserve here? You will conserve perimeter or length, right? So after some time, when the slope will be like when this tube will be accelerated horizontally. So if you accelerate like this, the liquid level will no longer be like this. It will rather become slant, something like this. So it will fall in one column and will rise in the other column. Something like this. So here the height will become, new height will become H1. It's the same thing. So whether it's a tube problem or a vessel problem, the way of solving is same. So you can write as the length of perimeter equals to same. So earlier the perimeter was H plus L, and now it is H1 plus H2 plus L. It's the same thing. So the same answer. And why we are writing like this? Because the area of cross section is same of the tube, so volume is conserved, and conservation of volume is as good as conservation of length. Because for a tube, the volume is L into area. Understood? The other part is same. So tan theta you can write as H2 minus H1 by L equals to H. That's your lookout. There is other way of solving, and which can give some answer directly. So the method 2 is basically pressure method. because it's a tube problem. So the best way is you enter from one end and exit from the other, and write the equation as you know. So let's enter. So how much you go below? Because the new position is like this. In the liquid has come down, right? So if from here, if you enter, if you go below, you will increase the pressure by. So you start from the atmospheric. You increase the pressure rho gh1, and you are here now. So you need to move to the left actually by L distance to go to the other end. So you can add, and because acceleration is towards the right, so as you go against the acceleration, what do you think? Pressure will increase or decrease? It will increase, so we have to add rho Al. That's simple. Rho Al. And then from there you go upward. So pressure will decrease minus rho gh2. You are back to the atmosphere. Cancels out, and what you can get is rho is also cancels out. So gh1 minus h2 plus Al equals to 0. And this gives you directly answer that A by G same as H2 minus H1 by L. Understood? And the conservation of length of the tube is anyway the equation will be there. So we always have the two equation, and the pressure analysis is the easy way to solve question in a tube. Okay, it is clear?
Yes, sir.
Okay.
Yes, sir.
So imagine we have a question like this. So we have a vessel in which there is a hole. This is so this is length is A. And the liquid level is filled up to height. C, A, B, and C, as you can see. So question is find the minimum acceleration required to prevent the liquid from leaking out of the hole. So this could be this way, this could be this way. I don't know which direction. So direction is not given. But what minimum horizontal acceleration we must impart to keep the liquid inside the vessel? This is infinite, so there is no, it will never leak from this side. So to find horizontal acceleration required to prevent liquid from leaking through hole. So try this question, then I'll solve it. Are you guys doing this question? Anyone?
Yeah, sir, 2 minutes.
Okay, solve it.
Sir, row is given.
So I hope this is done.
So is the answer B plus C G by
B plus C.
G into G by A?
It seems like, yeah, that should be the answer. So definitely there are two possibilities. You can either put all the liquid like this,
Yeah, sir, I did that only.
yeah, or you can put the liquid like this. But this is not advisable because this requires greater acceleration. Sorry. So we'll put the liquid on the left side. So that's the only way. So this side you can say H. This is theta. From the conservation of volume, what you can add? CA plus B is a volume or area, which is half into base into height. So we got H equals to 2C A plus B by A, right? So we got the H value from conservation, and now we know tan theta is how much? H by A, and this is equals to A by G. That's it. A not by G because confusing A. So A not turns out to be G by A into H, which is G by A into 2C A plus B upon A. Okay, so answer is not the same. 2C A plus B upon A square into G. That's the answer. Clear? So we are supposed to do the two steps. One is the conservation of volume. So all the liquid is on the left side, and this must be forming the slope like this. And if all the liquid is on one side of the hole, it will never leak, right? To put on the right side is like more challenging because you need greater acceleration because of the dimension. Okay. All right. Okay. So next is called rotating vessel. So let's say we have a kind of bucket. So the moment you rotate the vessel, what will happen? So in case of rotation, as you go away from the acceleration will increase or decrease or remain constant. So
Increase.
we know that the centripetal acceleration is omega square r. So as r will grow, definitely the acceleration will increase. So this is the question or case of variable acceleration. And because the acceleration will increase linearly, so we can say the slope of okay, so we'll see that. So the simplest way to solve the question is, let's take a okay, let me remove this also. I want to do more curvy picture. Mm, Can I make it curve? Yeah, this is better. Okay. So imagine we have a point on the free surface, because this is a free surface, so we know the property of free surface. So for the sake of writing, we can take the bottom, the deepest point where it makes a dip. So the lowest point we call it origin. Let's call it x-axis. And the axis of rotation we take as y-axis, which could be center, which could be here also. So you may create an axis of rotation here, here, or here also. So that I'm taking a symmetrical case. So the axis of rotation is also the axis of symmetricity. But that is not always going to be the case. So it depends on case to case. So here, axis of rotation is also axis of symmetry. Okay. So now you can see that as we go away from the axis, the liquid level will rise, right? Which simply means the pressure must increase. That we can understand or we can see also. I hope this is clear. Okay. So imagine a point P here on the free surface. So it will experience two forces. One is the centrifugal force. And because this is x distance away, because the coordinate is x, y. So what will be the acceleration of this particular, how much force it will experience? Dm omega square x. Because x will act as the radius, right? This particle is moving in a circle. You can realize this. Of radius x, right? And the other force is gravity, as we know. Because the slope is variable, so let's draw one line. So the net force along the tangent, along the free surface is always zero. So net force along the, and if you do so, what you can write is dm omega square x cos theta is equals to how much? Dmg sin theta. So what you get is tan theta equals to omega square x by g. It is same as a by g, but the a is not the same, right? Because as a will change, as x will change, a will change. Sorry. So because tan theta is omega square x by g, so this we can write as dy by dx, and therefore the dy becomes, and if you integrate from 0 to x some value, y becomes omega square x square by 2g. And this is a equation of a parabola, so we can say the shape of the free surface is like a parabola. Okay.
Yes.
And because we know the height of the liquid from the reference, we can find the pressure also easily, right? So once we know the x value, we can find the pressure. Okay. And what is the pressure? So let's say if we want to find the pressure here, which is x distance away on either side, it doesn't matter. So even if it is negative x or minus x comma 0, what is the pressure here? So we know the pressure here will be PATM plus rho gy, correct? And what is y? Y is y square x square by 2g. G will cancel out here. And the answer is very interesting. Rho omega square x square by 2. So now because you can add the pressure there, you can also add pressure anywhere else. So if you, let's say if you want to add the pressure here. So we know this is y, and rest they'll give you that how much deep it is this. You can find pressure there also, just to add rho gh. So in case of a rotating vessel, what is the rule? So as you go away from the axis, pressure will decrease or increase. Away from axis, pressure will
Increase.
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 Yeah, right. And towards the axis,
Decrease.
increase. So this is the rule, and the increase or decrease will be equals to what? So that will equals to rho omega square x square by 2. That is a meaning of that. Okay, so if you travel x away from the axis, the pressure will increase by rho omega square x square by 2, and vice versa. This is clear? So this time I just simply derive the formula. Now if I ask you, can you do the pressure analysis by drawing a capsule within the liquid and then solve it? Can you do that? Who will do the pressure analysis? Like I want a radial pressure analysis. That what happens radially when you go away, how the pressure will vary. So in the same diagram, you can do it. Radial pressure analysis. So anyone who would like to try this? No, okay, no. Okay, so now here is the question. So can you do the radial pressure analysis and how to do that? Think about it. If you don't want to do, just let me know. I'll solve. No need to worry. You need to learn to take the elementary, write the equation, and do things like that. And I can give you a small hint because you want to do the radial analysis. So you can go x and cut dx as elementary cylinder and then do that. If it still doesn't make any sense to you, not an issue. Don't worry about it. I'm there.
So we take x from the O point and then we take dx vertically.
No, don't take it from O point. Take anywhere inside the liquid from O. I mean x from the axis. So you can choose O. I mean from here also. That's okay. See, we are looking for the radial analysis. I want to what is the dp by dx? Like pressure gradient along x-axis or a radial direction. That's it. Okay, I think you're not doing it. Okay. So the simple rule is you just move X and make elementary cylinder like this. Because we are doing the radial analysis, we can do like this. Okay. Now this elementary point mass is moving in a circle of radius r. So the net force toward the center must be equals to MAC, right? The centripetal acceleration. So how to draw the FPD for the same if you want to draw at all. So let's say the pressure here is P because that's X and this is dx. So we say pressure here is P plus dP. That's very important. So the force will be into area, like you can just make it d as the cross-section area. That's okay. And this is the axis you're turning with omega. So the net force towards the center is definitely P plus dP into dA minus PdA, right? And now this equals to dm omega square r. So if you solve this, you'll get dP equals to, and dm you can write as rho dA dx and all those things. So you can see that the pressure gradient itself is rho omega square x, which is function of x. It's not constant. Earlier this used to be constant. Now it's variable. So the delta p is rho omega square x dx, and you can integrate. So when x is 0, we can name it some value p naught. When it can be anywhere. Okay. So this is O dash. Let's make it O dash. Let's call P O dash, or maybe yeah, P O dash. That's okay. And then pressure P. Then this is the formula. So what we are getting is that P minus P O dash is like along the radial we are taking the difference is rho omega square x square by 2. And this is what I'm trying to explain, that as you move away from the axis, pressure will increase. By what value? So if you look at the increment part, so P is P naught dash plus okay. So you can see that this value is the increment as you go away. So as x will grow, this will grow. So that is what we are trying to discuss, the pressure analysis. Okay. So we can do the same thing in case of tube also. And tubes are particularly famous. So if you have a tube, okay. So now we can do a lot of things. So let's say if we put, if we have an axis, let's say the axis is not symmetrical as we expect. It is somewhere here. So the graph is symmetrical about this. You can see clearly the liquid will be like the right side is quite far away, the left is quite close. So pressure will be less on the left side and more on the right side. Okay. So if we have a symmetrical positioning, then liquid level will be like something like this. Now this is of course due to lack of location. So graph is always symmetrical about this axis, and because the left tube is quite closer, so it will have the low level. So if I say this is H1, if I say this is H2, so we can relate the H2 by A and B because we know the answer. So H2 is basically how much? Omega square B square by 2G, right? And what is H1? Omega square A square by 2G, right? If
Yes.
you have to use the formula Y equals to omega square X square by 2G, right? Sorry. So definitely this is the answer like for H1. And the below part we can assume any height or whatever is given, and then we can, yeah. So they may ask you what is the difference of height. So H2 minus H1 is how much? You can see clearly the difference of height is this much. So height difference depends on the how far the tube is from the axis, and if it is equidistant, if A is equals to B, you can see that the difference will be 0, which means it will have same height, and that's logic. Okay. In most of the case, we can do the pressure analysis, and I would like to show you how to do that. So let's call the remaining height as h, just for the sake of writing, although it's not given, but we can always make some assumption like this. So the one method which is always applicable is the dive in and dive out. So you enter from one end and let's go. So the method 2 we can write as, so first you enter, dive in, how much? So you go almost h2 plus h below, so you can write rho g h2 plus h. I'm not writing the p atmospheric because that will cancel out, so I'm just ignoring now. In the next stage you will be moving, so you're here now, so what you do is you go towards the axis by b value, so it will decrease the pressure by rho omega square b square by 2. This is the decrease. Then you go away from the axis by a value, so it will increase the pressure by rho omega square a square by 2. Then you go up, which will further decrease the pressure rho g h plus h1, and that's equal to 0. If you solve, you'll get the exactly same answer. If you don't trust my words, you can do it. So the answer is same. So even the h which I assume, because that was not mentioned, gets cancelled out. So eventually you can see the difference of height on the two sides is always given by. So you can solve variety of answers based on this theory. Okay. So there is one more thing, but that I will solve only when you come across with the doubt in the class. So if you reach that level while solving numerical, you're going to ask me that question, and then I will answer. But we have done with the most part of it, which we need to know, called the acceleration. Accelerating vessels. So the buoyant force we have already discussed, but let's discuss once more. Uh, so I had given you the aquarium example. If the vessel is accelerating towards right, then we know that the lighter one will go right, but the heavier will go left. Okay. And if the rho is the density of liquid, so and d1 is the density of this one, and d2 is the density of this one. So we know that d1 is more than rho, and rho is more than d2. The density is. So this will be the situation that the green will go left. So we can prove it easily. White will go like this, and in both cases, the theta will be a by g. Okay. And if you draw the ABD for this, it will have the bond force for it will be V rho A, V rho G. But it will have pseudo force in the left side. How much? MA V D2 A, and below is gravity V D1 G. And because the density is rho is more than D2, so you can see the net force will be V rho minus D1, and this will be V this is D2 now. Why wouldn't D1? It's D2 everywhere. Okay. So D2, and you can see that the net will be what? So because the net force is towards right, so it will tilt right. The net force. Okay. So if I say this angle is theta, so you can write tan theta equals to VA rho minus D2 upon VG rho minus D2, and you can see that density of volume doesn't matter. So this is eventually A by G. Is this clear?
Yes.
Okay. So this is for the accelerating vessel part, and let's do one more problem for the pressure analysis. Okay. So you can very easily write the pressure in any kind of vessel. Yeah. So imagine this is a liquid in a container, and there is one small hole done to the end so that the atmospheric pressure can enter this vessel, which is closed from all sides. And let's call this as origin. Let's call below this as o-axis and left as x-axis. And this vessel is accelerating towards right with acceleration a, and I choose a coordinate x comma y. So what is the pressure at x comma y? So what is the pressure at x, y? Tell me.
So the x and y are acceleration. So what are x and y? Or
X and y
torques?
are the coordinate axis. A is the acceleration.
Okay.
I want to know the pressure at this coordinate. And the outside is the atmospheric pressure. Assume outside as atmospheric pressure. Done, guys. So what I have to do is very simple.
So T naught plus rho into under root G square plus A square and then X sine theta.
No, nothing like that. Don't take theta and nothing is there. So the simple rule is to reach this point. There are many ways. So you have to just move. First, you move horizontally, or then move vertically. That's okay. Or you can move vertically, then horizontally. That's up to you. So make sure that you either move parallel to x-axis or parallel to y-axis. Don't move elsewhere. So let's go left. So if I start at origin, if I go left, the pressure will increase by rho ax. That's it. And if I go below, it will increase by rho g y. That's it. This is y. And that's my answer. Is this clear? So you have to start from the origin, go left, add the pressure x. Because when we move horizontally, the pressure will grow by this value or decrease or increase. But here the increase. If you go below, use the vertical analysis, rho gh. Clear? The last topic,
Sir, your voice is cracked.
now.
So can you talk again once?
Okay, am I audible now?
Yes,
Yes.
sir.
Okay. So the last topic from the fluid statistics is called concept of center of buoyancy, also called meta center. Okay. So inside liquid, if you submerge something, then this is the part called submerged part, and this submerged part will have some shape, some volume. So what we say is that if we remove the submerged part by a liquid of density same as the liquid in which it is submerged, then the center of mass of the submerged part of liquid is called center of buoyancy. I mean, let me give you some simple example to understand this. Imagine we have a hollow tube. Okay. So L minus X, right? So now you can see that there is a submerged volume which is having the shape of a tube. So what is the center of mass of submerged part? Somewhere here.
L minus X.
Yeah, this is L minus X by 2. And this point we called center of buoyancy. And center of mass is the point which is exactly at L by 2. So for the entire body, the center of mass will have different location. But center of buoyancy only talks about the center of mass of the submerged volume of liquid. Like there is a submerged part, and if I remove the body and if I think of that part of water or liquid, whatever it is, then the center of mass of that part of liquid, assuming to be present there, is called the center of buoyancy or metacenter. Is this clear? Yes or no?
Yes, sir.
So center of buoyancy is different from the center of mass. If something is completely submerged and if it is also uniform in mass distribution, then center of mass and center of buoyancy may coincide. So imagine we have uh, an ocean or river, whatever, and now we have this is the front of the cruise or ship or boat. Let's say if it tilts like this, so how we can make sure that it will not topple? It will not topple on the right. It goes this way and it comes back. So you must have seen that the small boats will just swing right to left, but it will not. I mean, of course, dip. I mean, sink easily until you are not making like inverted or capsized. So how it is possible that it is prevented from sinking, although it's tilting a lot? So what mechanism prevent this, the stability of cruise or ship or boat or anything else? So the answer is very simple. In case of cruise, the bottom is made of iron and that's very heavy. So in case of cruise, the entire weight, almost you can say 90% weight is at the bottom, which is very, very high in value. All the machineries are at the bottom, so it's below the water level. And everything which you see above the water level, like the deck or the whatever they design, that part is very, very light in weight compared to the bottom because it's pure heavy machinery. So we have giant motors to run the cruise. Okay, giant motors, the biggest motor you can imagine. And the size of the motor of the cruise can operate more than 10 malls in Mumbai. That's so powerful. So it can provide that much electricity and that much everything else. Anyway, coming to this cruise part, so we try to keep the center mass as below as possible because of heavy machinery. It goes really below, and we have center mass somewhere here. Let's see. Now this part is the submerged volume, you can see, and it will have its own center mass, and we can expect it to be somewhere above somewhere. So this is called center buoyancy. So the net buoyant force always act at center buoyancy. And that is the reason that when the buoyant force act like this, the moment the cruise will tilt towards the right about center mass, this buoyant force will create a torque like this. And the moment it will tilt towards left, it will come on the other side and it will again make it vertical. So this is the buoyant force, which is kind of giving the stability to the cruise. So no need to worry. It will never sink, it will just swing left to right. Because the buoyant force will always become dominant. And as it will sink more, the buoyant force will increase further. And because the center mass is really below, we can always make it above the center mass and create more and more torque. So you might have seen some videos in which a newly built cruise is deployed in the river. Have you seen some video like this?
Yes, sir.
So it goes and it falls. It gets a lot tilted, but the moment it falls, the center mass is so below that the buoyant force suddenly topples and brings back to the original like position. So you can see that when they design, they keep track of the center buoyancy, and that is a takeaway. Like, so when you create a cruise or ship or boat, the bottom should be as heavy as possible. Like, in fact, the entire center mass should be at the bottom, and that is the case in most of the cases. That is the case. So generally, center mass is very below. In fact, it's inside the water itself, and no amount of tilt will make sure that it will topple. So the chance of toppling is very less. Of course, if there is a leakage of water, if water sinks in, then the body will have a shift in center mass and things will be very dangerous. So imagine a situation in which the center mass is above and center of buoyancy is below. See the dangerous situation. So the moment it will tilt like this, the buoyancy is here and mass is here. Gravity is acting anywhere here, and buoyant force will in fact help in toppling further, right? By creating a even torque which is supporting the toppling. So this boat will sink. This cruise will sink very often, very easily. So the rule is to prevent the sinking process, the buoyant force for stability concern, for stable equilibrium, the buoyant force must be above the center of mass. That's the rule. Understood? In this case, we have the opposite, and so it's dangerous situation. It will sink for sure. So the biggest problem is the leakage issue. Like if we have leakage of water inside the cruise, then the center of mass will start shifting, and then things will go haywire, and then okay, you know what happens. So how to keep the tube at equilibrium inside a liquid? How to make sure that the tube will not tilt, otherwise will remain vertically stable? So the answer is simple. If we have a liquid and if we have a tube, so generally the tube will not sink that much, but yeah, that's okay. So this is not a tube, it's some object actually. This is lightweight object made of density D. Okay. Density is D, and at the bottom of the object we attach a heavy metal pellet. Just as the heavy metal kind of disc you can just attach to the bottom, and this mass is M. Okay, and now I want to keep this in equilibrium. So even if you tilt, it will come back to the same vertical position without going other way around. Okay, so I need to give this also. So let's say this is X. So I don't remember the exact question, but okay, maybe L minus X. Okay. So what is the condition for stable equilibrium? Condition for stable equilibrium. So rule is center of buoyancy. Like if I choose this as origin, then y of center of buoyancy should be more than, or worst case equals to y of center of mass. Correct? So the center of buoyancy where we can find. So from O I can see clearly the center of buoyancy will be L minus X by 2. Correct? Center buoyancy is L minus X by 2, and this is more than center of mass. How to find center mass? So it's M1 X1. So M into 0 plus D into L into L by 2. m1 x1 m2 m1 y1 m2 y2 upon the total mass, which is m plus dl, density into cross sectional area also. So we have to write A. Let's say A is the cross sectional area. All right. So what we get is L minus x by 2 is more than density into dl square A by 2 m plus dl A. Okay, so if I invert m plus dl A by dl square A by 2, so we can say that m should be either less than this. I mean, if it is more than this, this is more dangerous. So we take the equality case to find the relation. I mean, of course, this is not the exact question, but there was a JEE advanced problem. So the rule is simple. You have to just make sure that the center of buoyancy is above the center mass. That's the only rule. So if you come across that question, I mean, JEE advanced old problem. So I have shared the PDF. You can search in that and you can solve. So we are done with almost all problem except the Bernoulli equation part. So that we'll do in the next lecture. Okay.
Yes.